Howdy. All right, check this out. Look how professional this is, huh? Get this far? Did you get this far? Okay, unplug and try again. See if it has an aneurysm. Fucking go, boys. All right. Depression averted. Why? Yes, there we go.
And it was brutal.
No, it's fine. I was confident the whole time.
8 to 0.
I was confident.
That's
He
crazy.
says as he didn't watch the first half.
Didn't want that good game, so. All right, so if I'm depressed, it'll be this weekend and you won't see me and I'll be normal by the next Tuesday. Otherwise, I'll be happy. And I'll go to the game on Monday. Might be a little over on Tuesday. And make no promises as to my mental health. I will try my best to grade your homework this week. I just finished grading my other class. So we can your application probably today. Where we go? I'm gonna go to Paris. Conference, so. That's the start of November, so if you guys want to just take that week off, but I think it would make sense if you're interested to having their guest. Okay. The new homework is out. Has anyone looked at it? So, it's gonna have a lot to do with what we're talking about right now. It's gravity stuff. And as we get into rings and as we get into small bodies, it's not the most complicated part of this class, but it's getting up there. Gravity is the least intuitive. And if you've never taken fluids before, fluids will be the hardest part of this class. If you have taken it before, then you have at least a little intuition how atmospheres work. But for the most part, gravity, I think, will be the hardest part for you. So we will do some examples today, trying to show the rings, and then we'll do the motivation. The rings will be the motivation, and then we'll talk about why they exist. Why are there resonances? What does it mean for there to be perturbations? Why are there gaps, etc. And after that, I think probably the right thing to do is just keep on gravity. And so then we'll talk about the 2-body problem, the 3-body problem, talk about satellites, talk about moons, the variant types of atmospheres. Okay. Okay. We saw this picture. The fool of me. All right, hold on. We were talking about Jupiter's rings, right? Said that all of the moons have rings. All the gas giants have rings. And here we'll see that these ones were detected almost immediately after they were also detected from the ground in 79. What you have to do, Jupiter's bright, right? There's a reason we call it the king of planets. And so that means that if you have faint rings nearby, they're very hard to see. So what you want to do is you want to look at and a strong absorption feature, which will make the planet look dim. So you look for a chemical species that is very present in Jupiter. And so the sun absorbs a lot of that chemical species light, and then maybe they'll just bounce off the rings. And methane is a really big one. So there's plenty of methane in the atmosphere of Jupiter. So that's CH4, and there's strong methane bands in the infrared. And so we can observe it. It'll look dark in the infrared, and the rings won't. Okay. There's a main ring. It's got two small satellites, Metis and ASTR, and they orbit on the inside and outside. Metis is. There's also a halo. It's about a factor 10 major. That's what Galileo saw. Pretty cool image. Kind of like what you would expect the ring system to look like. This is Jupiter from the back. Another way to do this, obviously. From Earth, the only way to do it. Okay. This isn't those methane band images. So let me see if I can show you this here. So methane has an absorption feature at 2.17 microns. So this is the infrared, near infrared. And you can see these bands here. So this is, these are different locations where there is methane. And of course, this is still, when you're in the near infrared, you're still getting emission from the planet. But if you have methane in the atmosphere, it's an absorbent. So this is blocking both light from the interior of the planet coming out and reflective light from the sun. See these little dots? You wanna know what the dots are? What's that? Storms, clouds, moons. Yeah, so these two here are cyclones. So they're clouds. There is no surface, right? And there is no place on Jupiter that isn't storms. So these are locations of upwelling from the interior, bringing up heat and particularly methane dam. And of course, what you can see here, this is the ring system. That's Metis that we talked about before. In the back side there's ASTR. ASTR. You get it. All right, there's the ring system. This is the same image. So this is the ring system. When you view it, and you just let your computer do an auto select for brightness. But what you can do, and what you should do with any image, is to blow out the scale, look at the noise. And so down here, these little dots, these are probably dark pixels. So these are when your CCD just arbitrarily decides that there's electrons there, you can think that it's warm. But over here, you can see that this is certainly the result of something. And this is part of that halo we were talking about before. So material that's diffusing off of the disk up around, and it's completely invisible when you are not looking for it. All right. So this is this sort of scale here. Here's the body of Jupiter, and this is an image, right? Real image, and then they stretch it to look at. Take a long image like this, and then cut it at each of those locations, and use a different stretch so you can see the difference in brightness. So right at the edge, of course, you have the standard image sensitivity, that one that we just saw that's backwards illuminated, right, by the Jupiter. So that's the atmosphere of Jupiter seen from behind. And there's that disk that we just saw. You crank it up 10 times, it starts to saturate nearby from the halo. Right? And as you go farther out, you see you have to go to 20 times sensitivity, and out here you can still see it at about 260 times sensitivity. And if your eyes follow this, right, you will notice shape. So it starts thin, gets wider, gets wider. Very gradual. Okay, so let me show you where everything is. Here's Metis and Adrastea out here. They're just right. One on the inside, one on the outside. Okay, remember that the ring is here. You just see it. Right, so it's not actually going this way. Doesn't touch the planet. It's like that. Shepherd by both. Okay. Out here, you have the Almathea Gossamer ring and the Thebes Gossamer ring as well. Okay. And these two bodies, there's a lot of moons. All of the ones you know and love are like here. And then there's a bunch of other regular satellites that are farther out in the solar system. Questions about this? Okay. These are very thin rings, very low density rings. And they have very low albedo. So the main ring here is, remember what the density or the albedo was for rock? What? Albedo, remember, going from 0% reflectivity to 100% reflectivity. Yeah, 0.2, 0.3 is good for rock. So if you have to do gray rock, it's probably 0.3. If you have to do standard looking rock, it's like 0.2. It's really dark basalt, maybe like 0.1, 0.15, right? So what's this here?
1.5%.
Yeah, that's very unreflective, right? Okay. And of course, they're very, very low density. Surface density is very low.
Does it have that low albedo because it's just transparent or because of competition?
Yeah, these are compositional, right? So the albedo comes from not the total amount of light going through, right? We don't expect that they're like glassy. We expect that they are just black. Okay. Neptune has rings. So there looked like there was arcs rather than smooth continuous rings. And in 1981, they first found this small moon, Larissa. And then in 89, they found Voyager 2, 6 narrow rings that completely encircle the planet. But unlike other ring systems that look thick all the way through, the Adams ring has sections to it. So remember, we were talking about what are the expectations we should have for a ring system. And we said that for Saturn, there's no reason to expect that there shouldn't be bunching up in certain locations. And Adam shows this, right? Here's Neptune's rings. What you have to do with this, of course, is you have to use something in the middle, walk it out in order to even see the system. So, what you can kind of see here, there's rings. 1, 2, 3, 4, at least. And then you have all these dots in. Some of these dots are stars, some of them are moons. Yeah, I don't know if I know. So Adams is the one up here. That's Arago, Lassell, Leverrier, and the French. So all of these are named after French. These are the arcs in the atom ring. And interestingly enough, they named parts of the arcs. What? Well, so like, I mean, how do you distinguish this piece from this piece? So it gets a name. So, you know what this is? Do you know what that means? Liberty.
Liberty, equality, and brothers.
Yeah. So this is what? Where does that come from? It's French, but where does it come from?
Oh,
Isn't that the
So this is a version of a declaration. This is the motto of France. So you know how we say like "e pluribus unum" on our dollar? It says like "together as one" or some bullshit like that. Theirs is liberty, egalitarianism, which is like equality for all, and fraternity. We know, right? Okay, so that's the name. That's liberté, that's égalité, that's fraternité. Okay, here's Neptune's rings, and here's the order in which it comes. You start at Neptune equator at 24,000 kilometers. You get Gale, and these are who they're named after. This is the discoverer of Neptune. Leverrier was the one who predicted Neptune's position so that Gale could find it. If you don't know the story about Uranus, the story of Neptune, it's pretty rad. They knew about Jupiter and Saturn and Uranus, and they said Uranus's orbit is even. And they said that there is precession in orbit that is unaccounted for by the current configuration of planets. And so then Leverrier went along and he said, oh, okay, well, if there was a planet like at this distance with this mass, it would account for the orbit of Uranus. And so they went, they looked, and he found Neptune to go. Lassell made a claim that he saw a ring, but he was wrong, but he still gets named after him, whatever. And then Arago, also a French physicist who encouraged Leverrier to predict this, and Adams independently predicted Newton's position before it was discovered. The cool thing about history is that both of these guys can share the glory that is finding them. Okay, there's courage. You know, they really went all out here, and then they just went for courage. You can drop French, but gives it no idea why. And you have these actually, if we go back one. Okay. So this is liberté, égalité, and fraternité. And this, if we look closer, we're not going to look in this section.
Those marks created because something's breaking up or being formed there.
We don't know. We don't know why. Yeah. The albedo is larger there. There is one of the reasons why it's difficult to take observations of these planets is one, because they're far away, right? So you are looking for something really dim, really far away. You would like to do occultations. So what that means is the thing we talked about before, where it passes behind the planet and you see the star get in. However, there is when you're doing a retrieval, for example, when you're trying to figure out how much stuff you just looked at, there is an issue with whether or not you're looking at a large particle, whether you're looking at a lot of small particles, or what the color of that particle. Right? And so all of these things can be degenerate. That is to say, they can make this one larger if you make this one smaller. You make this one smaller if you make this one larger. Right? So they have a connection. So we know that the albedo is larger by about a factor of 3 of the rest of the ring. We don't know. Makes sense. Okay. Things about them. None of the ring particles are big. And this is common in all of the observations that we've shown. They can't be solid, right? Maxwell showed that they can be solid. You know why they can't be solid? No. So even before we had observation, why can't you have like a solid ring?
Because the inner part of the orbit much faster than the outer.
Right. So it's shear. So if you build something, right, you have to be prepared for torsional flexing. So this is why if you watch any show TV thing, and your space station goes around the whole planet. Okay. Lots of rocks and dust. It's mostly ice, but it is lots of rocks and dust. We saw lots of moonlets and shepherd satellites. Usually they're not very big, and they're likely not circular. 20 kilometers is not nearly large enough. So even when we see something like Metis up close, it looks like a lumpy potato, right? There's complex but regular structure. So complex just means that it's not easily explainable, but there are gaps and there's reasons for the gaps. We'll talk about all of this. We saw this a little bit in the Keeler Gap. Do you remember that? There's a moon in the Keeler Gap. There's waves on one side and waves on the other. So we'll talk a little bit about how these waves form. First, let's talk a little bit about like why there's gaps, and then we'll talk about perturbations. Okay. There's not a lot of material. So while Saturn's ring is the most massive, it could make maybe a 200-kilometer moon. And that's probably what it was. Okay, so where do you get the rings from? Probably collisions of the moon. Giant planets and stars form from disks. We know this. We know that the Galilean satellites, the Jupiter satellites, the ones that are interior to the rings, they probably form from a disk. This is probably not leftover disk. This is probably material that is created somehow. The equator and the main moon system always line up with the ring. Okay. And the important thing here is this idea of a Roche limit. So we're going to talk about the Hill sphere, we're going to talk about the Roche limit, and these are words that you'll need to learn. This is essentially, you have some body, and we're thinking about it in the context of these tidal forces. Let's start. What is this crap? Stop writing stuff. All right. Yeah. Okay. So let's say you have some internal stresses. This is your moon. Why is it held together? Why is it so? So there's forces pulling it in, no? Okay. How do you pull it apart? No, that's how you smash it. How do you pull it apart? Can I do that? What do you mean?
Force is stronger than the force of gravity on the shape apart.
Right, so you want this piece here to come away. So I need a force this way that's larger than the internal force. And then this piece will be like, bye, fuck off. Okay. So when this force of gravity exceeds this force of gravity, that's the Roche limit. There's some body over here. Let's talk about tidal accelerations. Oh no, math. I came here to sleep. Okay. Let's draw this out formally. We're going to consider a moon, and we're going to make it of size delta r. That's going to be in the r direction from the bottom. Okay. There's Jupy over here. There's Jupy. This is going to be delta L. Let's imagine it's not in orbit yet. There's no angular momentum. And it's just at some distance on. This thing has some distance and it has an. Not called, it's called random arbitrary. So what's the acceleration? Felt here. Okay. What is the acceleration here? This is just a circle, right? Ignore the idea that this has. I'm asking, what's the acceleration here? Some distance away.
Gravitational cause of mass of the planet and the distance from the planet. So
That is the force of gravity divided by whatever object. Right. Good. Okay, what's the radial tides on this object? What does it mean for there to be tidal forces again? Well, that would be like gravitational, right? So what does it mean tidal? That's the result for sure. What? Yeah, that's Newton's third law. Why are there tides? Definitely some distance there, but that's not why there's tides.
same one object.
Stuff. There is no other object yet.
Right.
Yeah. So do tides need two objects?
Yeah.
Okay, so I'm gonna blow your mind. No. Tides are the result of differential gravity. Because gravity changes with distance, it's the perceived difference in gravitational pull that leads to tides. Recall that the first tidal bulge that points at the moon does so because it's closer than the center. There would be no tidal force if there were no center, because there's nothing to difference. Similarly, the bulge on the opposite side is left behind because the center of the planet is pulled more than the far bulge. So tidal forces require differential gravity. And we can calculate that without even considering the object. So we can make a general statement. We can say something like the gravity arbitrary acceleration that doesn't care about the mass. And we can use a differential. We say dGdr. How is that thing changing? How is this changing in radius? Now, if I go inwards or as I go outwards, right? This would be dr. Simple. Okay. And then by very disgusting math that you should never show to any mathematician, okay, you're going to say that the tidal radius for the tidal forces in the radial direction is this differential. And then to keep the units the same, you have to multiply it by dr. But okay. So how does this thing change with r? Please do that differential. R G N over R squared. What do we got?
So GM of constant, so it stays the same.
Good.
And then or you take it, you bring down this the two to bottom, which in that case it would go to the top. Wait,
No, just tell me what to write here. Don't tell me how to do the integral.
it's 2GM over R.
Okay. Good. Correct? Everyone has that? Everyone can do that in their head? Okay, you should do that in your head. Practice at home. Practice the following. D, E, X, X, the N. Right? Because even if I do something like that, okay. Okay, good. So we did it, and we can put this in here, and we get the result that I've written on the board. Minus 2gm over r cubed times delta r. Now, delta r in this particular circumstance is the width, or this half width. Called it delta r, so I divided it by 2. The azimuthal tide will be the tide. So remember, this is the way that we're thinking about these forces. Here I have a force that's pulling this way, and here I have a force that's pulling not as much, right? So those are the radial tides, and the net radial tide looks like. Which direction does the net radial tide? Towards the mass, right? Inwards. Okay. And then arrows are drawn. Big arrow. Okay. Now let's think about the azimuthal tide. That's going to compress the body. We start off by giving it this obscenely long oval shape. And here you can look at the geometry as opposed to needing a differential because they're at the same radius, right? And the only thing that's changing is cosine, right? Okay. So, we can write that one down as, G theta. Oops, no, G T theta. And I'm just gonna write the result, that's all that matters. Minus G M over R cubed delta L. Isn't that nice? Isn't that beautiful? Same form, right? Slightly different constants, but that's okay. These two. So what is the tide trying to do?
Trying to flatten out along the. um, and
Yeah, so I would say if you have something like this, it compresses it in the azimuthal direction and stretches it along top. This is before it starts orbiting. This is just an object living its best life. Don't think ring, don't think moon, think arbitrary ball of jello with no self-gravity. So you have some silly pipe, and you just put it here, and you watch what it does. And the next second starts as a circle, the next second gets compressed and pulled. Make sense? Okay. But now we obviously have to think about it. All right. So we care about things rotating. We almost never find stuff that's just a ball of goo with no forces on it, right? So now we really want to think about it with respect to the reference frame of those objects. Okay? So what does that mean? That means that I want to be standing, say, on the moon. In an inertial reference frame, say the one above where I watch the moon go around, there, of course, is force of gravity pulling me in. Right? And I can say something very second law of mass times acceleration is the radial velocity. Right? And I can set these two equal to each other, and I would say that's a circular orbit. Right? We've seen that before? Okay. However, if I'm standing on the moon, I don't appear to be moving. Right? So I don't appear to have any velocity. So therefore my acceleration must be 0. So gravity has to be balanced with a fake force. Called the centrifugal force. This is not real. It's from the fact that the reference frame is physically moving. In the inertial reference frame, we found out what was happening. We're going around a circle. From the moon's perspective, it looks like there's a balance of forces. Okay, so that is the balance of forces for an infinitesimal particle right here. Now let's give it size and see what effect this balance of forces really ends up happening, right? Okay. All right, that's fair. All right. Think back to this idea right here. These are gravities felt by the nothing God. Right? They're going to be moderated by the fact that if we go backwards one slide here, okay, you have the gravity of the body pulling it, but you have this rotation around that's throwing you up. Okay, that essentially makes you feel like there's maybe less gravity. In fact, you may think this no gravity. We don't sit on Earth feeling, for example, the sun's gravity, even though we're of course dominated. Okay. So here, what I want to show you is that in the moon's rotating reference frame, you have the force of the planet and the centrifugal force. And at the center of the body, right, this is perfectly okay. There's no tidal forces. So you have what's an effective gravity, which relates the period and the distance from the object. Sorry, this is actually frequency. If I flip this around, this would be exactly what's right? And that's that balance we talked about before. Circular motion, so on and so forth. Just so happens that you can do this with a circular body, and it's also true of an elliptical body, but Kepler is a boss like that. Okay. But now let's move away from the center. Let's move inwards. Okay. Now the G effective is not just this thing. Okay, because we have our normal radius right here, plus wherever we ended up. Remember, we have this piece here. So what I want to see is how does this G effective change with the orbital radius? Okay. And this is in the radial direction. So we have to make a couple assumptions here so that we can simplify some of this some of this math. Here what we're going to do is we're going to look at the effective radian. We're going to take the differential, just like we did before. This is the radial acceleration, but now instead of G effective, it includes the fact that we're rotating. Okay, so we do that. Good, perfectly good. We take the differential. We now know how to do those. And the question is, which of these terms is bigger? Or do you want to show that? Does that first line make sense? Can you reproduce it? No. We go back one more? Okay, let's go back one more. Let's start here. Oh, I just put them. Okay. Here's G effective. G effective, right? What you feel at some distance r is equal to, what's the first term? Okay, what is that? In English. That's not English. Also not English. I need you to explain it to a child or a cousin or mom. Almost there. So still quite not ready for a child or a family. Yeah, let's just imagine for a moment, what does that term mean on its own? Know here that A is the orbital radius, right? We could simplify this a little bit. Maybe I'll do this, okay? We'll do little r. What do we call that? Now, this is the distance, right, between the two bodies. See on that picture over there, the little r? What's this term called? This is not a distance term. It doesn't have units of distance. Is it?
Yes.
Is it?
It's not, because you're dividing by first force.
Body where the force of gravity.
Well, because I was thinking of it as like acceleration times mass, which is also divided by the distance squared. And it would be able to do it.
Okay, how do you, just answer this question, how do you write force of gravity? Okay, is that correct? No, it's not correct. Okay, it's also not correct. What's missing? The little m. So this is what? The force. So this is what? Right, I'll write it again. The acceleration. This is an acceleration. Okay. And it's acceleration of what? Gravity at r. This is the acceleration you feel due to the fact that you're at r. Okay, now this is going to confuse you, but you gotta remember this is not the same A. This is the A from our orbit. And this is not an acceleration. Maybe I'll change it just for you, special time, one time only. I'm not going to do this long term. Okay, not an acceleration. This term is an acceleration. This is not. Okay, good. Now the effective gravity that you feel is due to the acceleration at some distance plus sure, but remember we're using words again. You're right, that's what the terms mean. But what does it mean? Right, one more slide. What's happening in this picture on the right hand side? In the reference frame of someone standing right here, do you feel like you're moving in or out? Correct, everyone agree that you feel like from in or out? You're standing here on Earth.
Let's see.
You don't feel it. We're in orbit. We feel no velocity. We are moving fast. We feel nothing. That is because of a balance in our reference frame. The pull of gravity is balanced by the fact that we feel like we're being flung out. And those balance. This is fake. This is not a real force. But when we want to describe the accelerations that we feel in this frame, we have to consider fake forces that are due to the fact that the world is spinning and we don't perceive that. Right? So you have this here. This is the centrifugal acceleration, which is the centrifugal force, m omega r. Right? But the acceleration, you just get rid of what? What was that? For the acceleration. Very good. You get rid of the max. So the centrifugal acceleration is omega squared r. Hold on to that for 1 second. We just said we're going to balance the centrifugal acceleration with the acceleration due to gravity. And that will be the acceleration I feel. You better go. You better work. You better. God damn it. Why? Good. You should balance the acceleration due to gravity with centrifugal acceleration of being flung out. And what do we say they were equal to? 0. So that's what they're equal to. So now I have a relationship that tells me how fast I'm going around. So this term here, I can write in terms of how fast I'm going around in a circle. How quickly is my frame rotating, right? Okay. So I wrote it like this, omega squared A. And then I figured out that omega squared here is GM over A cubed. That's really convenient because I could just take this term and I can turn it back into
Back into acceleration.
right. Well, it is an acceleration, but I can turn it back into in terms of GM. Right? Let's write these all out. This is the orbital distance, right? So I can write this thing as GM for alpha cubed times alpha, which of course is
Over on the square root.
yeah. But now I want to be a little specific here. Let's clean this shit up. Now I don't want to just be at some arbitrary distance r. I want to be anywhere I want to be. So let me write this better. It's the same thing we just wrote. I said GM over alpha cubed, right? But now I'm going to use r here. And now I'm going to use r here. Okay. You see how that's the same description? What do I say? Acceleration of what? Okay, well. Of you at some arbitrary distance, right? So this is an acceleration at arbitrarily. Anywhere you want to be, that's how I describe it. We're very comfortable with that. This one, maybe not so much. What's this? One's way acceleration, which only depends on how close or far you are. Because if I'm standing on the rotational axis, it's 0. And I don't feel flung at all. The farther out I stand, the more I feel flung, right? Everyone agrees? So that's why r is only found here, and yet the whole frame is rotating with this speed, since this thing was omega squared, right? So this is the acceleration due to being flung at omega squared. C'est bon? Now we're cooking with juice. All right, we're good? So let's do a differential of this. Van Lentolman, please do this. You all, I'm not doing it. You do it. Are you doing it right now? You got it already?
You're talking about this, correct?
Yeah. Oh my God. Just doing derivatives in your head like that? You have it written down, that's. We got it? All right, once you do it on the board. Okay, go ahead. What books think? Oh, you have Dante?
Yeah.
So you have? What do you have?
3 GM 4 plus the GM off of 3.
But what it, then,
Okay.
okay, cool, no worries, that's okay, that's okay. What do you have? Here,
I haven't seen the inferior. I don't know which part, let's say, let's see.
so let's remember that GM over A cubed is a constant. That's a motion, right? So if I just wrote it omega squared R, would that be easier to take a derivative of? Right, because then the R would just disappear. So the derivative of omega squared R with respect to R is just omega squared. Okay, so Dr. Jeff here. Is something plus something. Okay, what were we finding out? What was the point of this? Yeah, we're finding out the differential acceleration due to the fact that there's a change in radius. So what I'm asking for is how does the gravitational acceleration plus the centrifugal acceleration change as I go in or out? We already saw that as I go in just with radius, that it changed like 1 over r cubed. Right? But now there's this fun little balance here. So which of these terms matters more? Wow. Why the left?
That's why. R3's changing. Okay. You increase the radius, it goes drastically down, but the constant is gonna stay the same.
Well, which one's bigger? I think got a 2 on it, right? So that must be bigger, right?
I'll say the constant will be bigger, because since the radius is on the denominator, the bigger the object, the smaller the number is actually gonna be.
Yeah, let's remember what some of these, we're saying the word constant and we're saying some words right now. Let's just really remember what they all mean. What does this little r mean? Yeah, so on which part of the picture is this?
That'd be, oh,
This thing here is. Let's go out to some point here. That's R. And what's this one? Yeah. A is bigger, right? So A is bigger. And dividing by a bigger number gives you a smaller number or a bigger number?
It's gonna be smaller.
Smaller. Dividing by a bigger number cubed is better or worse?
It'll get even more smaller.
Okay, we talked ourselves out of the constant? The constant? Okay. Good. Bada bing, bada boom. When we've done all of this, this is where you got to on your own. Is A and R roughly the same?
They're nearly identical.
Only in what circumstance? This good approximation for A and maybe equaling R here, is this true? That's R. That's little r, that's big A. Little a. Which one of these is a better approximation to say A is the same as R? This one, right? And in this case, let's say this is R. Yeah. What's the relationship between R and little? Big R, yeah, is much smaller. Then A is like R. Then I can simplify this by just using A. And how much do I have? I have 3. Let's use A. Now it's wishy-washy. And you ignore it when you're close. I mean, obviously. Is this gonna work for I? I is small compared to. But is this, but is it the distance, is it the size of Jupiter or is it the distance between them?
It's just the distance.
Okay,
I would say it wouldn't. It's not defined on Jupiter's.
so I'm putting on Jupiter size, I'm putting on Io size, right? Alright, so maybe that's something we're gonna check later. Compare Io's radius to its orbital distance. Okay. That's not all. Okay. So we clean this up. Then we can take this dr, we can do the same little trick we did before, we can multiply it by delta r from earlier, right? It's gonna be small. Right? This divided by a very large number, gonna be really small. So it's not gonna matter in a majority of cases. Why does it matter in these cases? Because you have icy bodies that can deform more rapidly. You have eccentricity, which leads to large changes in A. And you have resonances that we'll see and do repeated forcings at repeated times, so that builds up energy in the system. Okay. Oh, I got it. Here we have remember we talked about this internal battle. We had the force interior to the body, and now we've calculated the radial force away from the body. So we can set that equal to each other. So this one here, we recall, this is gm over r squared. This is the mass of the little body trying to hold itself together. When this is equal to the tidal force trying to pull you towards the moon, even while you're in orbit. And that's really important here, right? Then I can relate these two distances, try to put them together. Right? Can you do that? So we have some objects in here. Yeah. So on this side, this is the mass of the body. Right? The little body. Okay. This is the radius of the big body. And the density of the big body. You need those. If I rearrange them, I get. I'm just going to show you. One. There you go. This very straightforward. This A here is a distance. This is the body, the big one. Take that body, multiply it by 144%. Then take the ratio of the density. If it's the same density, let's say 2 terrestrial bodies, this is 1. So let's interpret that really quickly. We have the Moon-Earth system. If I bring the moon as close as 1.5 Earth radiuses, will it be broken apart? One vote for yes. Do people understand the question? Should I repeat myself? Okay, moon, Earth, both wrong. Assume they're the same density. Don't do that calculation. Okay. They start out here, like 80 or 90 times away from each other. I bring them like this. And the whole time we've been talking about, at some point, the force here on the moon being pulled to the Earth is going to outperform the internal pull of the moon. Okay. So now I bring them here. And this is 1.5 times the radius of the Earth. Does the moon survive? Yeah. Okay. All right. So calm down. So you've actually found an issue with how we describe the hill radius, but we're gonna brush over that for a while. Okay. So in practice, you do need modeling this, but this is like a benchmark. Okay. So just assume that hasn't been violated. even though it clearly hasn't violated the circumstance. The reason we talk about this is that when we talk about something like the Hill radius, which is this specific radius at which gravity of the other object becomes dominant over gravity of you, is because it is a very helpful tool, a back of the envelope tool, to determine relative distance. Now, in practice, you need to know more things, right? You need to know what the composition of the object is. You need to know what their relative distances are, whether there's eccentricity. We have said nothing about them, right? We just took the ratio. Right? Okay.
But still,
So in fact, it will survive because it's outside. 1.5 is greater than 1.44. The moon does survive. No, not really. But in this idea, it should. If it gets to 1.44, that's when it should start to break up. That's how we interpret it. And it's a sphere. Okay, so it doesn't matter which direction we're looking. If you're orbiting this way, if you're orbiting this way, it doesn't matter. If you're at 1.44 times the radius of the Earth, you're gonna break up. And if you're interior to that, gone. Right? You're just part of the Earth at some point. So when you build a disk that makes the moon, it better as hell be outside of this radius. If you have a tight disk, right, then you're never going to form a moon. So you'll notice one thing that we saw in all of these ring systems is a gap, an interior gap. Ever wondered about that one? It's going to be this big. It's going to be hill size. See, okay, I said the word hill there. That's the person, not the object. Okay, all right. These are hill spheres. Okay. This is also called the Roche limit. If you account for the stretching of the moon. So this number gets bigger. This is the Roche limit. This is the hill sphere. Okay. So there it is. There's the distribution of satellites. All safe. Almost there. All right. This assumes some things. So let's take the whole system, let's shrink it all on the same size, so they're multiples of the radius of the object. So this is 1, right? Okay, so that's 1, and then this is Jupiter, and of course all of your planets are down in here. This is Saturn, this is Uranus, and this is Neptune. Okay? And in these ring systems, it's a little hard to see here. These the dash line versus the dotted line. The dotted line is a little trickier to see. This is the dotted line. Here's the dashed line. Dotted line, dashed line. This one is in here. Dotted line, dashed line. Dotted line, dashed line. Oh, I think those are flipped actually. Okay. Do you know why we care about these locations? What does the dashed line mean? Synchronous planetary rotation. Synchronous planetary rotation means where are you orbiting with the same period as the surface of the planet? The surface. So if you're standing here and you're orbiting at this location, then you're going to see the same part of Neptune for your entire life. Similarly with Uranus, if you're here, you're going to see the same part of Uranus your full life. For Saturn, Saturn is rotating faster, so you have to be closer. And here you see the same part of Saturn your whole life. Similarly with Jupiter, Jupiter's rotating very quickly, and so you. Now, Roche radius for objects, 1 gram per cubic centimeter, that is what type of object? Purely ice, right? So just ice. So you'll notice that that's not so bad out here. You know, it's outside of the entire ring system. Okay. Here, it's like smack dab in the ring system. Okay, that's a little weird. This entire ring system, obviously bigger, is way outside. And here, this one is smack dab in the middle of A. Okay. Here's all these little moonlets of Uranus, including Miranda, cute little Miranda. And this one's in between Rosalind and Linda. We're gonna use one called that. Okay. Okay, that's it. That's all we have time for today. I didn't realize that I would be that slow. I have the other one ready to go, but I guess we'll do it another time.